All right, so this is Math 383, complex analysis. This is lecture 2. So I was just talking about the 3 different possibilities for the types of lectures which we will be doing this week. So you have a chance and you can get back to me. How many of you have seen The Wizard of Oz? One scene in The Wizard of Oz is how I feel about lecturing. It's the scene when Dorothy is trapped and you have the hourglass with the red sand of like the blood color. And as soon as it is all down on the bottom, she's dead. This is how I feel about the 50-minute lecture. All right. So anything we can do to use the 50 minutes we get 3 times a week more efficiently is a good thing. And so I really want to be exploring how can we do all this better. Okay. So I will always be, yes.
I think one of your screens.
Yes, I have to give myself permission to record myself. Thank you. What's interesting is you don't always see on there what I see over here. I can actually see the little arrow, but when it then eventually hides itself on that screen, but still shows up over here. But yeah, when you see things that I don't seem to be aware of, please point them out. All right, so what I want to do today is talk a little bit about the review of what is the complex derivative, talk a little bit about the Cauchy-Riemann equations, and talk a little bit about the connection with Green's theorem, which you may have seen in multivariable calculus, you may not. Not all of the paths here go through that. If you want to know more about Green's theorem, I have the warp speed lecture in a day from one of the times I taught Math 150. So it's a really fast 50-minute version of just going through what you need. If somebody wants to throughout the semester to keep track of how often we say Cauchy versus how often we say Riemann, I would be very curious. Cauchy is going to be winning in the early part of the semester. Riemann is going to come on strong as we go further. Cauchy-Riemann equations is really nice because if you miss any of them, it doesn't really matter. It's not going to affect who wins. But we will be seeing these names again and again and again. All right. The other thing I want to talk about is, especially for those of you who will be taking things like the GREs and stuff like that, you will sometimes be in a situation where you're not allowed to look things up and you need a formula quickly. And so if you approximately remember a formula, can you do a few quick checks to then figure out which of the candidates is the one that happens to be right? And so I'll talk a little bit about how you can go from your rough memory to what is actually true. All right, so let's start off with the complex derivative. So as always, we start with the definition. So it's f prime of z is the limit as h goes to 0 of f of z plus h minus f of z over h. So really doesn't look that different from what we did in one variable. The difference is that we now have more paths. So this was the old, and this is the new. And we have to be able to handle all paths like that. Now, just because we can handle all paths doesn't mean all paths are going to be equally useful for us. There are still some preferred directions. What are the preferred directions, do you think, for our complex variables, for our paths? Yeah, basically hold the real variable fixed and just come down the imaginary line, hold the imaginary variable fixed and come down along the real line. So we're still going to have some preferred directions. And this should be very similar to some of the things you saw in multivariable calculus with the partial derivatives. Okay, so we did some examples. With a little bit of work, you can get if f of z is z to the n, then f prime of z is n z to the n minus 1. Right. So that's a really nice exercise. We did, I think, n equals 1. You can do it by induction. There's lots of different ways you can do it. There's some really nice backdoor ways if you want to think about it and you want to avoid induction, you can do that as well. We did if f of z equals z bar, then it is not differentiable. And your z bar is x minus iy if z is x plus iy. It's the complex conjugate. So not every function is going to be complex differentiable. We often say holomorphic for complex differentiable. And the advantage of saying holomorphic is it sounds more prestigious. Yes, when you talk to other people, oh, you only, a little bit highfalutin. It's really just saying differentiable. Now later, we will learn another word. We will learn the word analytic. Does anybody know what analytic means? Yes. Yeah, analytic means it's equals its Taylor series. And then we learned that in complex analysis, the words holomorphic and analytic are actually the same in one variable. If you're differentiable, you equal your Taylor series. If you equal your Taylor series, you're differentiable. One direction is not that hard, right? If you equal your Taylor series, it's probably not too hard to show you're differentiable, given that the Taylor series is sums of derivatives of your function. The content is the other direction, that once you are differentiable, you actually equal your Taylor series expansion. All right, so we will frequently write f of z in an abusive notation, sometimes as f of xy. This is not technically correct, because if we write it like this, f is a function of one complex variable. I'm now writing it as a pair of real variables. But you know what? It's such a common thing, and it should be clear from context that we will often do that rather than the more accurate f of x plus iy. And if we write x plus iy, then there's no problem. We still have f of just one input. But to abuse notation, we'll often just write f of xy. And frequently we'll write f of z as u of xy plus I v of xy. And so this is the real part, and this is the imaginary part. Okay. And again, I am regarding now u and v as functions from R2 to R, and f is a function from C to C. So it's always good to know where things live. Okay. So one interesting question would be, if I tell you stuff about the real part of a function, how much freedom do I have in the imaginary part of the function? Well, if my function can be arbitrary, then I have complete freedom. What kind of restrictions do you think we're going to put on our function? We want our function to be holomorphic, right? Thank you for not saying differentiable, which is what I was actually thinking in my mind. Right? If we want our function to be holomorphic, can I always give you a real part which will lead to the same holomorphic with an appropriate imaginary part? If I have a real part that leads to something that's holomorphic, is there a unique imaginary part? How much freedom do we have? Can anybody tell me at least whether or not there will be one or infinitely many choices of the imaginary part that will lead to it being differentiable? Could you have just 3 choices of B? It would be unusual. Why do you know you can't have just 3 choices of B that work? Well, but remember, I can't change the real part as well. So what imaginary part can I add that's not going to change the real part, that's not going to affect differentiability? Constant, right? This is the same as the problems from calculus. If I give you a function, the derivative is unique. But if I try to go the other way, what function has this as its derivative? So when I'm trying to think, if I want things to be differentiable, I do have a little bit of freedom in terms of what I'm adding for the imaginary part. So other than just shifting by a constant, do I have any more freedom, or is everything now uniquely determined? All right. So now let's look at the Cauchy-Riemann equations. So let's assume f is holomorphic. So its derivative exists. So f prime of z equals the limit as h goes to 0 of f of z plus h minus f of z over h. Can somebody give me a good path to take?
Like along the way.
So let's go along the real. So we go along the real. So f of z plus h will be f of x plus h comma y. So we're going to go along the real path. Okay, so if I put that in, I will get the limit as h goes to 0 of f of x plus h y minus f of x y over h. What does this equal? Good. Be more specific. The partial derivative of what? Good. The partial derivative of f with respect to x. And that would be du dx plus I dv dx. Because f of xy is u of xy plus iv of xy. Okay. Any other paths that's worth trying? Yeah, let's go along the imaginary. So it's also going to be the limit as h goes to 0 of f of x y plus h minus f of xy. Now we're going to think a little bit about what comes down below. So what would be down below? So would it be IH? So we have z is x plus iy, z plus h is x plus I, y plus h. So what are we changing by? So the change is I times h, with h being a real number. So we should be dividing by IH. Okay. So important safety tip, complex analysis is only fun until someone loses an eye. Old joke. So it's the limit as h goes to 0. Oh, we already got the limit, so there's no need to do this. We pull out the 1 over I. And what are we left with? So yeah, df, dy. Now, instead of writing 1 over I is the same as negative I. So this would be the same as negative I times du dy plus I dv dx. I'm sorry, dy. Or it's the same as negative I times I is 1. So it's the same as dv dy minus I du dy. Okay, so now we have two beautiful expressions. We have this expression over here and this expression over here, and these are equal. We're assuming the function is differentiable. We're assuming the function is holomorphic. So since the function is holomorphic, it doesn't matter which path I use. They have to be the same. So we now know that du dx plus I dv dx equals dv dy minus I du dy. So what's the only way two complex numbers can be equal? They have equal real parts and equal imaginary parts. You think of a complex number as a vector, as a tuple. So the real parts must be the same and the imaginary parts must be the same. Okay, so we then get the Cauchy-Riemann equations. So we get du dx equals dv dy and dv dx equals negative du dy. Or if you remember your notation from before, it's u sub x for the partial with respect to x equals v sub y, and v sub x equals negative u sub y. Right. So these are the famous Cauchy-Riemann equations. What we've just shown is that if the function is differentiable, if the function is holomorphic, then it satisfies the Cauchy-Riemann equations. What else would you like to know? Yeah, other way. So it turns out it goes both ways. So if f is holomorphic, then Cauchy-Riemann equations hold. If Cauchy-Riemann holds, then f is holomorphic. And we'll make that clear. So we've only proved half of the theorem. The other half of the theorem is in the book. All right. So what do we get? I should hopefully be able to just quickly cut and paste. Interesting if it takes less time to write it than to cut and paste. But all right, so here's the Cauchy-Riemann equations. So imagine F is holomorphic, and we know U of xy. How free is V of xy? Do you think there'll be more than one V that works? Or do you think V is now going to be determined? Yeah, it's basically determined up to constant. I know how V changes with X. I know how V changes with Y because the derivatives of V are just now the derivatives of U, and we know the derivatives of U. So how free is V? Only up to a constant. So if there's a solution, any other solution would differ just by a constant. All right. All right, who would like a quick quiz right now where you cover all your notes and all your books, and I give you a quiz right now? And your entire grade will depend on whether or not you can reproduce the Cauchy-Riemann equations perfectly. How many of you know approximately, well, it involves partials of U and partials of V, right? What are the Cauchy-Riemann equations? So this is for those of us who will forget things very quickly. And, it involves something. So I know there's a relationship between U sub x and what? And V sub y. And I know there's a relationship between U sub y and V sub x. And then the question is, where is the minus sign? Well, if we forget where the minus sign is, all we have to do is choose an example and then do the computation. What might be a good example? Try f of z equals z. And if that doesn't work, try f of z equals z squared, right? One of those should work. Well, if I take this, then I would get u of xy equals x, v of xy equals y, right? Because f of z is u of xy plus I v of xy. What's the derivative of u with respect to x? 1. What's the derivative of v with respect to x? 0. What's the derivative of u with respect to y? 0. What's the derivative of v with respect to y? That's equal to 1. So if we are absolutely sure that there's a minus sign, will this tell us where the minus sign is? Yes, because Vx is related to V sub y, so there can't be the minus sign. So this is enough. If we know that there's a minus sign, this works. So if no, there is a minus sign, we're good. The problem, of course, is we have a 0 equals 0. When we look at, you're trying to compare the derivative of u with respect to y and the derivative of v with respect to x. So if we're not entirely sure, this is not the best example. If we do z squared, this is going to be x squared minus y squared plus 2ixy. And so now you would have u of xy is x squared minus y squared, v of xy is 2xy. And so this would be a more interesting example. So when you do this, you would now get the derivative of u with respect to x is 2x. The derivative of u with respect to y is negative 2y. The derivative of v with respect to x is 2y. And the derivative of v with respect to y is 2x. And that's a much better example. So yes.
When you say if you know there's a minus sign, do we mean in our
No, that I know that there's when I have the relationships between the partials, that, I know that there's some minus sign, but I can't quite remember which of the pair has it. And so if I know almost the functional form, this is enough to get it. If I have a little bit less memory, doing a more interesting example is enough to give me a good sense. As an aside, the rational root test, if I give you, f of x is an x to the n plus dot 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 plus a0 equals 0, and f of p over q equals 0, then p divides and q divides. Does anybody remember what p divides? Will you bet the life of the person behind you on this? I do like the fact that you're checking, Well, let me see who it is first. How confident are you? Did anybody ever see Legally Blonde? All right, very similar to that scene here, okay? How can you check? Can anybody give me a polynomial with integer coefficients and a rational root? All right, x plus 2 is a little bit basic because you've got some ones and one. So I want something a little bit more complicated. Let's do 3x plus 2. And then the root is negative 2/3. So you would see that the p is going to be dividing the 2. Okay, so p probably divides a0 and q probably divides an. And again, this is the power of, if you approximately know something, you're trying to remember what it is. If you can look at a special case, that's often good enough. All right, so we have the Cauchy-Riemann equations. And here, we can make them a little bit smaller. And we'll just put them over here so they stay on the board. All right, now, why do we care about the Cauchy-Riemann equations? Well, the goal of all of this is to be able to integrate. And we learned in Calc 2 that we could integrate certain nice functions, but only if we could find antiderivatives. It turns out analysis is integrating functions that give you a value of 0. And then we tweak that to things that do not give 0, but do not give 0 in a very nice way so that we can pull in those contributions. So the key tool is Green's theorem, which we're going to generalize. So out of curiosity, how many of you have covered Green's theorem in 150 or in some of the class? How many of you have never seen Green's theorem or a proof of it? Okay, so we do not need to know Green's theorem for what we're doing. If you have seen Green's theorem, it's nice motivation. I remember when I was a sophomore in college, I was visiting one of my friends from high school who was a freshman at Harvard, and I went to their multivariable calculus class, and because that's what you do as a math geek. And I left thinking it was a wonderful lecture. The professor was relating all this stuff from multivariable calculus to electricity and magnetism and whatnot. And then everyone's looking at me, go, oh, okay, so it wasn't a good lecture. And we went into the class thinking we just don't know math. We left thinking we don't know math and we don't know physics. Is that all the motivation he was doing was stuff that just didn't resonate with them. And so why are we doing all this? Well, it's a nice generalization of some of the stuff from multivariable calculus. This has tremendous applications in certain parts of physics like electricity and magnetism. We will see in our class applications with evaluating integrals. If you haven't seen Green's theorem, it's absolutely fine. This is just motivation. If you sadly haven't seen it, the motivation is going to be a little bit weaker. So here we have a function p of xy, another function q of xy. We have some curve in space, and we want to integrate over some curve gamma. And the result we get is the integral of p dx plus q dy over gamma. And the closed circle around this means is a closed path that goes around and returns from where it started. I am going to be very vague and just say gamma is a nice path. It doesn't intersect itself. We can spend a lot of time in the semester talking about that. Is equal to the double integral, we'll call the region inside A over A of dq minus dp dy dx dy. So a line integral is equal to an area integral. Does anybody recognize this quantity here? It has a nice name. It's the curl. So this is the curl of our force. As again, I don't want to go into too much detail. How do you prove Green's theorem? So a lot of mathematics is about trying to figure out what is the best shape to study. Can somebody give me good candidates of shapes that are nice? Squares, or the more generalized square known as a rectangle. Okay, so squares and rectangles, what else do we have? Circle, what else? Triangle. So these are the three good contenders. They fit together nicely. And we will see later in the semester that for a lot of things, we're going to work with triangles rather than squares or rectangles, because it's a little bit easier to get some triangulations. But squares and rectangles, it's another nice way to develop a theory. Here we will do things with squares and rectangles. Okay. Let's try to prove Green's theorem on a nice region. If we can't prove it on a nice region, odds are we're not going to prove it in general. And then the hope is that if we understand it for a nice region, we can push that forward. So let's take some kind of rectangle. So here's the point AC, BC, BD, and then this would be AD. And we always, always, always walk in a counterclockwise fashion. And so we're going to try to prove Green's theorem in this range. All right, so I'm going to just analyze the double integral of dq dx. What do you think the double integral of dq dx is going to end up equaling? When you look at this, the double integral of dq dx should equal not 0.
It'd just be like b minus c times.
Well, no, I'm trying to prove this equality here. The line integral of p dx plus q dy is the double integral of dq dx minus dp dy. What do you think the dq dx? Yeah, the line which yeah. So I'm probably going to hopefully show that the line integral of q dy is just going to give us the dq dx. Yes.
I'm not sure I understand what it means when I would start with function.
Oh, I'm giving you two functions, p and q. And I'm just considering, I can consider like the vector field, p of x comma q of y, p comma q. And so really, this is almost like your function p plus iq is how it's going to look when we complexify things. But I can just look at this as, a quantity. Now, you have the double integral of dq dx. We only have two main techniques in multivariable calculus. Change variables and switch the order of integration. Which would you rather do? Integrate dq dx with respect to x or dq dx with respect to y? Yes, can you give me a function whose derivative with respect to x is dq dx? Q, right? It's screaming at you, please integrate me first with respect to x. And of course, to make sure we don't discriminate, we have dp dy, which is screaming just as loudly, I'd like to be integrated with respect to y first, if you don't mind. Okay? So let's integrate dq dx. So writing it out, we're going to integrate first with respect to x. And I love to be explicit in my bounds. X goes from a to c, and then y goes from b to d, dq, dx, dx, dy. And so it's the integral, y goes from b to d. And when I integrate dq dx, I get q. So it'll be q of xy evaluated at x equals a and b dy. So this is going to be the integral, y goes from b to d of q of x. Oh, yeah, the bounds there, that's right. I know, yep. So y is going from c to d. And x is going from a to b. hopefully I have erased everything I need to erase. Thank you. All right, so y goes from C to D, x goes from A to B, y goes from C to D, x goes from A to B. So we would have, when x equals b, we get q of xb minus q of xa dy. And now if you remember multivariable calculus, when you've seen something like this before, what is the change in y as I go from the point AC to BC? 0. So I'm going to split my curve into 4 parts, gamma 1, gamma 2, gamma 3, gamma 4. Over here, there's no change in y. So over here, dy is 0, and here on dy is 0. And similarly, oh, yep, and they should be, yep, thank you. So it should be q of b comma y, and then q of a comma y. All right. And so on gamma 1, the integral of q dy is 0. On gamma 2, what's the integral of q dy? That's just this piece over here. This is just the integral over gamma 2 of q dy. On this piece, there's no contribution. And on this piece, well, normally I would integrate from AC up to AD, right? I'm going from AC up to AD. If I want to go in the other direction, it costs me a minus sign. Beautiful, I've got a minus sign right here. And so that's going to cancel. And we get that this is going to be the integral over gamma 4 of q dy. So this whole thing is just the integral over gamma of q dy. So this is meant to just be a sketch of the proof as to why everything works out. This is not meant to be a full rigorous, just if you've seen some multivariable calculus before, hopefully this gives you some idea of why Green's theorem is true. All right, this is for a rectangle. If we want to do something in general, let's say we have something like this. Well, in the interior, I can chop it up like this. And if I zoom in a little bit, to something like this, in each box, I'm going in a counterclockwise manner. And what you notice is a side like this, any interior side, I traverse twice. So interior side, like this, we go, once we go in this direction, once we go like this, it cancels out. So all the internal segments, all the internal line integrals are going to cancel out, and it's going to be pushed to the boundary. The area integrals will just all sum and add up together. And so this is why it somehow comes down to what's going on the boundary. The difficulty now is we have to figure out, well, how do we handle, what's going on as we get near the boundary? That becomes, a little bit of a challenge. And to just show you how careful you have to be, theorem. All curves between 2 points have the same length. Any thoughts about this theorem? I'm sorry that it's not true. Okay, would you like me to prove it to you? Yeah. So here's 2 points. I'll draw a curve connecting them. Given that I've made so many mistakes today, you should probably watch this carefully. What I'm going to do is I will take a very small polygonal path. And you agree that in the limit, as I take smaller and smaller and smaller steps, that this is going to become a closer and closer approximation to the curve. I take all the vertical pieces and I shove them to the right, and I get that line. I take all the horizontal pieces and I shove them down, and I get this line. So independent of the curve I take, if I look at the length of the polygonal path, it's going to converge to the same quantity. All right, maybe I need my curve to be monotone. What's wrong with this proof? My hypotheses, what hypotheses? Yes. Okay, so what sense does it approach the curve? Right, so if I zoom in, and really see what's going on. Point-wise, any point on the right is extremely close to a point on the curve. But the distance of these two red segments is not the same as that distance. So we often use ds to denote the infinitesimal distance. And it's not ds equals dx plus dy, but it's actually ds is the square root of dx squared plus dy squared, or ds squared is dx squared plus dy squared. This is Pythagoras. And so I can't just say that even though the curves are close, the associated quantities are close as well. You've got to be very careful in arguments like this. It's the Pythagorean theorem that goes into play here. Anybody know the most famous movie that basically misquotes the Pythagorean theorem? I will leave that as cultural extra credit. What movie greatly misquotes the Pythagorean theorem in a very, if it was done deliberately, it's wonderful satire. So this is what you need to be very careful about. This is why we need analysis. Because it is so easy to make these heuristic arguments. Now, the conclusion here was so absurd, I'm not going to sneak this by you. The danger is when the conclusion seems plausible and I do some arguments like this and can try to get it by you. We used to say that our freshman physics professor could easily approximate away special relativity, and the argument would have seemed very rigorous and whatnot. So you have to be careful as you do this to make sure that you do not have any assumptions. All right, so let's see Green's theorem to complex. So let's let f of z equal u plus iv, and dz will be dx plus I dy. And so now f dz, integrating over gamma, and again, I'm just basically playing extremely fast and loose with the math right now. That would be u plus iv times dx plus I dy. All right, so that would be the integral. Let's just do the real part. So it'll be u dx minus v dy plus I. And now the imaginary part would be v dx plus u dy. Yes. Okay, here's good. So here is Green's theorem. Should probably written in green, but it's fine. So here's Green's theorem. So if we want to use that, what should we take for P and Q? For this one, take Q equals what? Good. And over here, it would be P equals V and Q equals U. So now we need dq dx minus dp dy. Well, that's going to just be dq dx is negative dv dx, and dp dy is going to be minus du dy. And what is that equal to? 0. Why is that equal to 0? Cauchy-Riemann. And so let's just paste the Cauchy-Riemann in here. Right? And so by Cauchy-Riemann, du dy is equal to negative dv dx. So this whole expression has to be 0 by Cauchy-Riemann. And similarly for other ones. So we basically get that the integral of f along a closed curve is 0, if f is holomorphic. So integral of holomorphic f on closed curve is 0. Okay. This is a real rough sketch of the proof. Don't worry, we'll spend many days doing things in great technicality. This is actually my least favorite part of the semester because as we're slowly proving the Cauchy formula, I can never remember. So just what regions have we proven it for so far? Okay, I can do it for a triangle, but not a rectangle today. Okay, great. Okay, so today, at the end of the day, you can use it wherever. All right. Now, if every integral was 0, of course, that would be of limited use. There are some integrals that are not 0. So for the integral not to be 0, what must be true about f? It's not holomorphic. Good. So we need f to be non-holomorphic somewhere. And as long as there's some place where it's non-holomorphic, then some interesting things can happen. And so the typical thing is the following. I have some nice closed curve like this. And of course, I will do it counterclockwise. And imagine I have a couple of points where f is not holomorphic. I'll say, this point over here, this point over here, and this point over here. And f is holomorphic everywhere else but those points. So what I can do is I'm coming along my curve, and I'm going to come over here. So I'm walking like this, walking like this. I go around, and then I come back down, and then I continue. And so I do this about each and every point. So come up, come down, go around, and then same over here. Now there's a couple of questions you can ask at this point. Is there actually a small gap? Yes or no? What's the distance around those? Well, I can maybe make this of size epsilon, and I can send epsilon to 0. And similarly over here, I can have a radius, it could be the same epsilon. And then radius of circles tends to 0. Okay? Now, if you look at what's going on, whoops, oh dear, I do not want that. If you look at what's going on in the region inside here, what is true inside this yellow region? So f is holomorphic. So if we call this maybe gamma 1, gamma 2, gamma 3, and gamma, the integral along gamma plus gamma 1 plus gamma 2 plus gamma 3 of f dz would have to be 0. Because in this region, it's holomorphic. And then as I take the limit as epsilon goes to 0, these will cancel. And I'll be left with small little integrals along the circles. And so this is going to yield the integral along gamma of f is equal to the integral along negative gamma 1, negative gamma 2, negative gamma 3 of f dz. And negative is actually good because the way we're going around these circles, what direction are we going around those circles? we're coming down here, we're going counterclockwise, then we come up and we go along the circle about the point. We go around. So the negative makes counterclockwise. So the result is that, this is a big picture of where we're going. If we have 3 points like this, we can draw circles about each one of these. And now these circles are oriented in the counterclockwise manner, C1, C2, C3, gamma. F is holomorphic, save the bad points. Then the integral of f along gamma is the integral of f around C1 plus the integral of f on C2 plus the integral of f on C3. We have just reduced integration over general curves to integrals over circles with arbitrarily small radius. So only need circles with small radii for our integration curves. That's not bad. So what we're saying is that if we could understand integrals along circles, we can understand things in general. So let's try to understand circles. Let's integrate along a circle of radius r of z to the n dz. So we're taking f of z is z to the n. So I can write it r e to the I theta to the n is r to the n e to the I n theta. As we are running out of class time, but we'll make it, let's keep wearing our engineering physics hat. If f of z is z to the n, what would dz be? Doesn't matter what f is, right? I'm just asking what's dz. My function f of z doesn't impact what dz is. dz is just the derivative of z. So if z is r e to the I theta and r is fixed, dz should be I r e to the I theta d theta. And again, we're just arguing really fast and loose right now. So this integral should be like the integral theta goes from 0 to 2 pi. Z to the n is going to be r to the n e to the I n theta times I r e to the I theta d theta. So I make mistakes. Okay, good. So when you see this integral, what do you want to do? Yeah, take out the constants. So we can take out an I, we can take out an r to the n plus 1, and we have an integral from 0 theta equals 0 to 2 pi of e to the I n plus 1 theta d theta. And if you want, that's I r to the n plus 1, integral theta goes from 0 to 2 pi of cosine n plus 1 theta plus I sine of n plus 1 theta. So if you integrate sine or cosine along a complete cycle, what do you get? 0. So if I integrate it over many complete cycles, what do I get? 0. There's only one choice of integer n where this is not going to be 0. What is that choice? -1. When n equals -1, you just have the cosine of 0 plus I sine of 0. So this is equal to, when n equals 0, we get 2 pi. So it's 2 pi I if n equals -1, 0 if n any other integer. So we've just figured out how to integrate the function z to the n. If I could say the integral of a sum is the sum of the integrals, I can now get any series expansion. And in using the really fast and loose mathematics from over here, I can now get the integral over any curve by just looking and seeing what is the -1 Taylor series term in its series expansion. So this is the high level fast introduction to what we're going to do. This was the non-rigorous day. We will now do it rigorously. Wednesday's class, as I said, is going to be, a review of whatever. It can be any class. Probably it will be real analysis.